Hi everyone. First and foremost, I want to thank the organizing committee for this event. I'm so excited to share our ideas with you, and I can't wait to hear your feedback. I also would like to thank the other co-authors who contributed to this project with us one by one. My classmates from Computer Science Department of 9 University, Melike, Oruc and Goksun, Beren, Usta, PhD student from University of Antwerp, Hussein, Marah, and Professor Moharram Challenger from University of Antwerp, and Assistant Professor Baris Tekin Tezel from 9 University. Before starting the presentation, I would like to introduce myself. It's Onur Alhas. I'm just a fresh graduate from Computer Science Department of 9 University. And I have Melike, who is both my classmate and one of the co-authors of this paper. She will be accompanying me during this presentation. Since this presentation is our first presentation experience in a such large corporate organization like FETSIS, we apologize in advance if we make mistakes. Let's move on to introduction. Here you can see the main headings and subheadings that I will follow in our presentation. I will mention all. Moving on to our main goal. As all we are aware, online shopping has started to become a necessity, as well as being a great convenience, especially with the effect of the pandemic. Although we know how effective and facilitating it is for us, it is also a profitable transformation for companies and specifically for market chains. While there are good aspects of this revolution we live in recently, there are also a few aspects that can cause some difficulties. The part we are dealing with is the human errors and the decrease in the efficiency that the warehouse staff can make in order to provide these online orders to the people, to the buyers. Based on this idea, we desire to develop order picking robots using the shortest path algorithms created in the warehouse environment. Let's move on our problem definition. Starting from the starting point, the robots will visit the randomly generated coordinates of the products, and then they will return to the starting position. Therefore, according to our scenario, problem is the traveling salesman problem, as all we can understand. We will run this TSP solution in two ways, greedy and heuristic approaches, and we will compare the results. While the ultimate goal is real robotics with a physical real environment, but it is often very helpful to run simulations before doing research with real robots as well, physical environment. So that's why we used VBots as the simulator. We were just between Unity and VBots. Then Professor Baris Tekin Tezel advised us to choose VBots. Then we did it. Java was used as programming language since future studies will be adapted to the agent development framework in Java in the physical environment. I will mention about it later. Our related work. There are many applications for robots in warehouses in the literature, to be honest. We wrote most of them in our paper, but to give an example, a study was conducted to create an autonomous robot with an RFID application. As a result of the application, the robots identify the items by reading the labels on them, picking up these items, and then going to the desired location to store the item. As a contribution to these studies, a layered CPS development model is proposed to create an automated order picking warehouse storage system for online shopping in a simulation environment. With the simulation environment and the proposed architecture, both object avoidance and collision detection algorithms are introduced and implemented. Different shortest path finding algorithms are applied, and their performances are evaluated according to the solution of traveling salesman problem for product picking the optimum time. Let's see our architecture. We created the architecture of our work as shown in the figure. Our main goal is to compare the shortest path algorithms. Yeah, if we start from the middle, we used VBots as a simulator. At the same time, by using VBots, we can easily use physics engines from hardware abstractions, such as sensors and actuators, GPS, and many stuff to locate robots and the obstacles, for example. As I said before, we chose Java as the programming language because we aim to make the robots do the same scenario in the physical environment by using them in our future work, such as Java Agent Development Framework called Jade. Then after creating algorithms for features such as collision avoidance and obstacle avoidance, we run the simulation. So to be honest, our dataset is a bit simple. Let's move on to our dataset. As I will explain in the next slides, we recorded the travel time in seconds of the robots between the coordinates that we randomly generated using Python. And we used these results to evaluate the efficiency of the algorithms, basically. I will explain them in the upcoming slides. We have some couple of methods for our specific physical environment. Before comparing the shortest path algorithms, two important features had to be made for the robots to move. One of them is obstacle avoidance. For this, 8 infrared sensors of the EPUC robot were used by us. We modified and we coded those sensors. And these sensors scan an area of 4 centimeters and change direction when they see an obstacle. When these sensors do not detect the obstacle, the robots basically continue to move on their route again. Another feature is collision avoidance. In particular, this is one of the fundamental building blocks of the CPS architecture, obviously. We made this feature, which is also of great importance in our work, with the supervisor library of VBots. This library allows us, the robots, to get to know each other. Basically, in this context, the communication of robots was ensured by developing algorithms. As a result, in the study, it was ensured that the robots did not collide with other robots by messaging both obstacles and each other as well. And our methods for traveling salesman problem. So methods that we used for our scenario, of course, those are not ours. We used 2 methods, which are greedy and A-star algorithms that aim to find the shortest path. Basically, the difference from the other is that one does it greedily to find the shortest path, and the other does it with a heuristic approach. However, neither the greedy algorithm, which we created based on Dijkstra, nor the A-star algorithm is the algorithm that offers suitable solutions for TSP. That's why we have modified both of them a little bit. Those are all explained in our paper. Therefore, one of our aims in the study was to convert them to TSP. Euclidean distance was also used when calculating heuristic distances of the roads. I will show our proposed approach in our scenario. So we started with creating and designing the simulation in VBots. We have added some couple of obstacles and some kind of things to make robots work harder, to make it more real. And we generated some random coordinates by using Python, and we run A-star and the greedy algorithm, and the result of these 2 algorithms, we took them as our data set, and then we compare the results. So I will show you a portion of our experimental result. So here we can see a chart, a graph, bar chart. We wanted to show you some of the comparison of the results we got, basically. According to the results of the early experimental simulation studies, if the number of products to be collected by the robot is less than 80, it seems more efficient to use the greedy algorithm. However, it has been observed that A* performs more successfully when the number of products is more than 80. Here we can easily see that as the number of nodes increases in our scenario, the A* algorithm working with the heuristic approach starts to give better results than the greedy one. We can clearly observe this from our experimental results. And to conclude, in this paper, we designed and developed a simulation application to simulate the real behaviors of cyber-physical system embodied as robots working in a warehouse or a store, or it could be anything that we can imagine. Shortest path algorithms are modified, deployed, and tested in the simulation application. I explained the test results in the previous section. According to this context, we have decided in which cases the heuristic approach, which is the aim of the project, and in which cases the greedy approach gives a better solution. And let's move on to future works. Actually, we have many plans for future work. At this stage, we have implemented these systems separately, but we want to implement them as a whole in the near future. But our first goal is to physically create this scenario with physical robots. We are planning to use Lego Mindstorm in the first place. Although we cannot say this current scenario completely, but we can say that a slightly modified version, a slightly simplified version of our VBot scenario, because I think it is not possible to have a huge environment, real environment with many obstacles and robots as well. In addition to that, it is to realize the building blocks of the project, such as collision avoidance and road planning, by providing communication with digital twin. Our work in this area still continues. PhD student Hussein Marah from University of Antwerp is working for this to implement digital twin on our scenario. And that's all from me. Thank you all for listening to me again.
Thank you very much. Very nice presentation.
Thank you.
I don't see any hands raised or any questions, but do you plan to continue this and look at other algorithms? Are you thinking of devising new algorithms, or?
Yes, indeed.
Plans you have?
Yeah. Currently, we have been working on 2-opt algorithm to see it implemented in our scenario. We have been searching for new algorithms to get a better wide results in order to make a good decision. Yeah.
Okay, very good. Do we have any other questions? I don't see any in the chat, and I don't see any hands raised. So thank you very much.
You're welcome.
Thank you to everyone who spoke. Oh, Thomas has his hand up. I'm sorry.
Do you hear me now?
Yes, we can hear you now. Good.
Yeah.
Okay, thank you. I was unmuted, so now I can ask a question. The question is, could you tell some details about this environment? So how many robots, what was the structure of the rules, etc.? How complicated it was according to, let's say, testing your solution?
Do you want me to show you right now? I can show you if you want.
Okay, if it is possible, so it will be nice. How many robots, etc.?
So we can have n robots, to be honest. Then I will show you to be more clear.
because it is really interesting. However, as I think it is a kind of the first step for future development. So as Mike told you and other algorithms, however, in which way you can scale up to this real application in the future?
This is our simulation. So now there is a star algorithm working out here without any obstacle. This is our simulation environment. Here is the randomly generated nodes. You can consider them as a product in a warehouse. It could be like a banana or a can, something like that. And it travels between the coordinates within this scenario. This is without obstacle. And I can show you with the obstacle one right now. Greedy. Here's the greedy algorithm. And we have A star as well. And we have been working on true opt algorithm to see it is implemented. It is a bit slow. Sorry for that.
Oh, no problem.
It avoids the obstacle, as you see. And sometimes we're having some problems regarding obstacles because it's a bit hard to run the algorithm with obstacles. So I have better thing to show you.
Yes, but the question is in the warehouse you have shelves and some paths to get to the product on the shelf. So in this case, there are some routes, not only all possibilities to move. There are some directions which you must choose to get there. So in this case, this algorithm will be a little more complicated.
So I just show you the theoretical parts.
Yeah.
So there are ways to get stuff, a product off the shelves on Vbots, and those things are just to be made. So those things are just how to say that?
Under development. Okay.
Yeah. So yeah.
Okay. Thank you. But it's interesting. Thank you very much.
You're welcome. I will keep you guys updated. I will do my best to the next FETSys conference. I will try to do my best to submit our future work. I mean,
that would be interesting.
Thank you.
Very good.
Thank you, everyone.
Thank you.
Thank you for having me.